G'day. So here we are talking about these things called robots in education. Um, as many of you may know, they're not new. Robots have been around for a while in education. They're getting more sophisticated, obviously, but they've been around for a while. So just want to touch on something before we go into the robots per se, and that is if you do a search on Google for I don't know, new trends in education for argument's sake, or robots in education, you'll often get this sort of thing, which is, 5 trends, 6 trends, 17 trends, pick how many trends you want. Bunch of people sitting around a table looking at what the trends in education are going to be. They come up with a bunch of trends. It might be robots, it might be AR, it might be VR, it might be artificial intelligence, and they say, oh yeah, this is going to be really big. They then publish something in a shiny brochure, and all the manufacturers say, oh, it looks like robots are going to be really big. We better start making robots. So they all start making robots, and then they start marketing those to schools, and the schools say, oh, this is the new cool thing, we better get robots. And of course that becomes a self-fulfilling prophecy after a while. So what I want to look at here is where robots can be deployed in the K-12 scenario, and what some of the gotchas are, and some of the benefits, and some of the things that might need to be considered, and look at some examples of things that can be used within schools. But we really shouldn't go any further without talking about this bloke. Seymour Papert, an amazing guy who was a student of Piaget, that most of you should be aware of by now, and then worked at MIT, Massachusetts Institute of Technology, with, amongst other people, Mitch Resnick, who is the guy responsible, or one of the people responsible for Scratch. So together with a lady called Cynthia Solomon, Papert worked with a computer language called Logo that some of you may have heard of. Now bear in mind this is in the late 60s, so there's not too much in the way of graphics other than graphics that the students would build themselves, which on a green screen is not particularly amazing, but it was very useful for him to study how children think. And in fact his books, Mindstorms and The Children's Machine, are seminal works in what's called the constructionist constructionist philosophy. And there is a link down there to where I got these images from. You'll see those on each of the slide if you wish to go further. So now, throughout this presentation, there'll be a number of videos, and if you are short on time, you just want to skip through, you can just skip through those videos, and I'll try to remember to give you an idea of how long each of these videos would be. There will also be some links, and I'll put them into a separate location or a separate place that joins or is alongside this video. So when we start talking about why it is that we're doing these sorts of things in school, if you've got the time, you might be interested in looking at this. This is 40 minutes long, but so therefore I haven't included it in this. But the guys that we're looking at there, the two guys in the black shirts, are on the left is Bruce Dixon and a guy from Melbourne who started a company called Modern Learners after working to get laptops into the hands of every teacher in Victoria. The guy on the right, a guy called Will Richardson, is a pretty well-known blogger in this space and also works with Bruce in Modern Learners, or worked with Bruce. He's retired now. Mike Fadick is the guy there in the check shirt, guy who started a thing called Taking It Global when he was really young, works with the UN, works with Indigenous peoples. Really worthwhile having a look at Taking It Global, it as in IT. And the fellow to his left, on your right, is Gary Stager, who worked with Papert with children at risk, basically in a juvenile prison in Maine. Investigating what they could do with these people that society had essentially thrown on the rubbish heap. And there's be a link to his paper on that as well that you'll find accompanying this. So what is a robot, and why the hell do we use them in teaching? So most people will have some concept of what a robot is, and it's usually something which moves around and has some sort of human anthropomorphic, if you like, appearance. So it could be an assembly robot that's putting together cars, or it could be the robot that goes around and sweeps the floor, or it could be C-3PO or R2-D2, as you can see here, or it would be that scary looking lady that's actually a robot that's about to take off the mask. And there's a big thing about whether or not robots are going to replace teachers and replace people in the workforce, and we'll talk a little bit more about that later on. But where you'll see robots in class, in schools, is particularly if you're in a K-1 to K-2 environment, and sometimes they're still using these in 3 and 4, you'll see something like this, which is used for simple movement. So you press the buttons and then off they go. That's basically what these things do. So why would you do that? Well, you might want to be looking at kids' understanding of procedural texts, because they've got to tell this thing what it is that they want it to do. And that might be going out and going through a grid, for argument's sake, which has the numbers from 1 to 5 on it. And the kids have got to make the robot travel to 1 and then to 2 and then to 3 and then to 4, and give instructions which are fairly simple: forward, back, left or right. And the left or right goes in 90-degree swings, and then they can pause it. There's a couple of interesting things here. Not only are the kids looking at procedural texts, which are useful in English and literacy, but they're also looking at spatial orientation and terminologies, which are more appropriate in mathematics. But you've got to think about this from the perspective of the child. Like all of these things, it's worth considering the environment and the context in which these things are being deployed, and we'll talk more about this as we go through. So as far as a student is concerned, if I'm going to go forward, whose point of view is that? What does forward mean? Because two students sitting opposite one another on a mat where they're going to move these things around, if they're facing one another, the forward for one is the reverse, go back for the other. So that spatial orientation has a lot to do with whose point of view it is. And the other thing that's interesting about this is that you can't edit your program or procedure. So if you say to go forward 2 steps and then turn right or whatever, and it turns out that 2 steps isn't enough and you really need to go forward 3 steps, you've got to cancel, clear, press the X, and then go and do the whole lot again, which is a bit frustrating, but it's also very difficult for kids, really down in the K area, unless they have something written out on a piece of paper so that they can copy it back again, because they forget. Who wouldn't? So that's an issue. The other thing at this basic level, and this goes right the way through everything really, is how do you power these things? So, everyone thinks that rechargeable batteries are fantastic because teachers will put the batteries back on charge at the end of each lesson, won't they? No. Inevitably, you'll drag this out of the cupboard because you're doing it period 2 on Tuesday. You'll take it out 5 minutes before the period, or maybe at the beginning of the period, and you'll find that the last user didn't charge them. They take a fair amount of time to charge, so there goes that lesson. So you probably need a plan B, or even better, I found, is a drawer full of AA or AAA batteries or whatever it is that the thing uses. That's a really worthwhile thing to do. If we take the next step up and go to something like this, called a Sphero, that some of you would be familiar with, one of its advantages is that it can do some pretty amazing things. It's got a little screen on top there that you can see, and it can move all the way, do lots of different things. You can program it, but you can drive it as well. One of its disadvantages is it's only got rechargeable batteries, and these batteries don't charge by plugging them in. They charge by induction, sort of like a watch or a QI charger for a phone. So whilst they've got some really good points that you can use to drive these things around and do the sort of expanded version of what you might have done with a B-bot or a Blue-bot or an Ozzo-bot or any of those other simple bots, the difficulty with these things is that because of their construction, unless you've got a carpeted floor with a very short nap in the carpet, as sort of like those sticky carpets that you walk over in pubs, although hopefully in your classroom there'll be less stickiness, they're not particularly reliable or have actions which are repeatable. Now, I'm not trying to discredit these things. They're a wonderful thing to use within class because you can do a lot of things with them, including painting or choreographing a dance. Lots of really interesting stuff that you can do with them. But to provide accurate and repeatable actions, you've got to calibrate them. And that's a really important thing and a great thing for kids to have some experience with calibrating an instrument before you use it. But also have some understanding of the fact that it's not always going to be a precise or accurate result in your coding. So a lot of kids, I've noticed, just go back to driving it around, sort of pointing on they're usually programmed with an iPad and moving their finger around to move it around the classroom. But that takes away that whole idea of repeatable and accurate and precise movements. Now, it's interesting, even Sparrow's website itself contains a discussion of what the difference is between precision and accuracy, which is a worthwhile thing to read. But this seeming failure or falling down or flaw in this design is actually something that's really useful, because you get the kids used to the idea that just because you tell a robot to go forward 10 paces, how does it know how far 10 paces is, and how reliably will it do that? So whilst it may go and get a cylinder head and put it on top of a motor on an assembly line, what if it moves at 1 millimetre the wrong way? Is that going to make the engine no good anymore? So again, it's talking about context and what is the environment within which these things are going to work. If you're looking at this from a secondary perspective rather than primary, there's a great link that I'll put at the end of this, which is learning the motion uncertainty of spherical robots in different environments. It's something which is really useful for quite advanced kids up around the 9, 10, 11, 12 range within schools. If we go to how do we actually control the movement, we can say go forward 50 and all that sort of stuff, but often the environments either change or are not predictable. So one of the things that's done in a lot of classes, and you'll see a Lego bizzo here that's following a line. So it's called a line following robot for fairly obvious reasons. But whilst that's a really interesting exercise in logic or algorithm development, not many robots in the real world use those things anymore. They tend to use something like this. This is a simple QR code because the robot in question, a robot called Kai, which we'll look at later on, only needs a few instructions, and therefore the complexity of the QR code doesn't need to be very complex, I suppose. The robots that run around the Amazon warehouse and various other robotic warehouses tend to use these sorts of things to work out where they are and where they've got to go to. That nowadays tends to be taken over by something which is a little bit more accurate, perhaps, and more real time. We're looking here at a thing called LiDAR, which is sort of like radar, except it uses light. And if we know how fast light travels in air, then we can work out using that formula where things are in relation to us by just measuring how long it took for the light to get reflected back to us. Because the light has to go out and come back. That's where the division by 2 comes in. And what that does is to give if you've got a number of these scanners that scan not just one point but several points, then you can end up with this sort of thing. This is the way that your phone, if you use facial recognition, this is the way the phone does that. It uses a thing called a LiDAR scanner, most of them anyway, to scan your face and measure where things are in relation to all the other things. If you've got a MyGov account and you're going to put in your photograph into that, it will use the LiDAR scanner in your phone, if your phone has it, to scan your face for its own facial recognition. Quite an interesting bit of business, but as we'll see, LiDAR it's only suitable in certain circumstances. So we're going to have a look at a couple of videos in a second, notably this little fella here, which is called a Q robot, CUE. And the video that comes up is about 1 minute 20, or please feel free to skip ahead.
After playing, programming, and learning with Wonder Workshop's Q, we find the following positive points.
Woo! Back online!
Besides its main app, Q by Wonder Workshop, you can program Q with other tools from Microsoft and Apple, which makes it a very versatile toy for education. The battery lasts 2 to 3 hours, and the charging time is just 1 hour. This allows you to keep playing without big breaks. Q motors are fast, powerful, and precise. It is able to move at high speed, move around on carpets, and perform movements with a fair degree of accuracy. On the other hand, Q did not convince us on these points.
What's up there?
The chat mode with Q leaves much to be desired. Some answers are very limited or meaningless.
Are you with me?
Besides paying a good amount of money to get Q, you must pay more within the app for new games and avatars. Q isn't compatible and does not have as many apps as its predecessor, Dash, which gives you a limited gaming experience. In operation and features, Q is an improvement over Dash. You were able to program it in different ways and turn Q into a useful educational tool.
So there's a useful sort of review that you can pick up at lots of different places, including things like YouTube, which is where that one came from, and I'll put the link to that at the end as well. Notice the sorts of things which they picked up. Now, you won't get the that in the glossy magazine that comes from, or the glossy brochure that comes from that company. And notice that even though they're doing the pros and cons, it only takes 1 hour to recharge. And there's not too many periods in a school classroom that goes for longer than that. Anyway, there you go. One of the reasons why you might want to introduce the robots, as we said earlier on, is for things like understanding procedural text, but also to get spatial awareness and blah, blah, blah. A lot of what you'll hear in the press is so that the students can get a job in STEM. I'd much prefer to think of it as school as not just a pipeline to employment, but really getting kids to understand their world. How does their world work? Because increasingly robotics is coming into, and computational thinking is coming into our world all over the place, and no doubt you're aware of this. Now we're going to look at self-driving cars in a minute, or one aspect of self-driving cars. But of course, robots don't necessarily move around on wheels. You go to the US, and I think one's open in Australia now, where you can get pizzas that are manufactured or made by a robot. You can get flapjacks made by a robot. There are robots that you can buy if you've got the money that you can say, make this recipe for me, and it goes and gets everything it needs, puts it in the oven, times it, gets it out, and then presents it to you on a plate, which is kind of cool. But probably the biggest thing that's around at the moment is this thing about auto-drive cars. So we talked about a thing called LiDAR earlier on. Let's look at whether or not Elon Musk, who appears to have the lead in self-driving cars, let's see what he's got going for him here.
In the case of LiDAR and the March of Nines, isn't there an example, and I want to just get to your slam on LiDAR because it's pretty clear you don't like LiDAR. In this,
LiDAR's lame. LiDAR is lame.
That isn't there like a case where at some point 99999 down the road where actually LiDAR may be helpful, and why not have it as some sort of a redundancy or backup? So that's my first question. And the second, so you can still have your focus on computer vision, but just have it as a redundant. And my second question is, if that is true, what happens to the rest of the industry that's building their autonomy solutions on LiDAR?
They're all going to dump LiDAR. That's my prediction. Mark my words. I should point out that I don't actually super hate LiDAR as much as it may sound, but at SpaceX, SpaceX Dragon uses LiDAR to navigate to the space station and dock. Not only that, SpaceX developed its own LiDAR from scratch to do that, and I spearheaded that effort personally. Because in that scenario, LiDAR makes sense. And in cars, it's friggin' stupid. It's expensive and unnecessary, and as Andre was saying, once you solve vision, it's worthless. So you have expensive hardware that's worthless on the car.
So you might be familiar that there are at least two sensors in the car. One is vision, cameras, just getting pixels, and the other is LiDAR that there are a lot of companies also use. And LiDAR gives you these point measurements of distance around you. Now, one thing I'd like to point out, first of all, is you all came here, you drove here, many of you, and you used your neural net and vision. You were not shooting lasers out of your eyes, and you still ended up here.
We might have.
So things went well.
Can't speak for everyone.
So clearly, the human neural net derives distance and all the measurements and the 3D understanding of the world just from vision. It actually uses multiple cues to do so. I'll just briefly go over some of them, just to give you a sense of roughly what's going on inside. As an example, we have two eyes pointed out, so you get two independent measurements at every single time step of the world ahead of you, and your brain stitches this information together to arrive at some depth estimation because you can triangulate any points across those two viewpoints. A lot of animals, instead, have eyes that are positioned on the sides, so they have very little overlap in their visual fields, so they will typically use structure from motion, and the idea is that they bob their heads, and because of the movement, they actually get multiple observations of the world, and you can triangulate, again, depths. And even with one eye closed and completely motionless, you can still have some sense of depth perception. If you did this, I don't think you would notice me coming 2 meters towards you or 100 meters back, and that's because there are a lot of very strong monocular cues that your brain also takes into account. This is an example of a pretty common visual illusion where you have, these two blue bars are identical, but your brain, the way it stitches up this scene, is it just expects one of them to be larger than the other because of the vanishing lines of this image. So your brain does a lot of this automatically. And neural nets, artificial neural nets, can as well. So let me give you 3 examples of how you can arrive at depth perception from vision alone. A classical approach and 2 that rely on neural networks. So here's a video going down, I think this is San Francisco, of a Tesla. So these are our cameras, our sensing, and we're looking at I'm only showing the main camera, but all the cameras are turned on, the 8 cameras of the autopilot. And if you just have this 6-second clip, what you can do is you can stitch up this environment in 3D using multi-view stereo techniques. So, no, it's there we go. So this is the 3D reconstruction of those 6 seconds of that car driving through that path. And you can see that this information is very well recoverable from just videos. And roughly that's through process of triangulation and, as I mentioned, multi-view stereo. And we've applied similar techniques, slightly more sparse and approximate, also in the car. So it's remarkable. All that information is really there in the sensor, and just a matter of extracting it. People drive with vision only. No lasers are involved. This seems to work quite well. The point that I'd like to make is that visual recognition, and very powerful visual recognition, is absolutely necessary for autonomy. It's not a nice to have. Like, we must have neural networks that actually really understand the environment around you. And LiDAR points are a much less information-rich environment. So vision really understands the full details. Just a few points around there's much less information in those. In the construction sites, what do those signs say? How should I behave in this world? The entire infrastructure that we have built up for roads is all designed for human visual consumption. So all the signs, all the traffic lights, everything is designed for vision. And so that's where all that information is, and so you need that ability. Is that person distracted and on their phone? Are they going to walk into your lane? Those answers to all these questions are only found in vision and are necessary for level 4, level 5 autonomy. And that is the capability that we are developing at Tesla. And this is done through combination of large-scale neural network training, through data engine and getting that to work over time, and using the power of the fleet. And so in this sense, LiDAR is really a shortcut. It sidesteps the fundamental problems, the important problem of visual recognition that is necessary for autonomy. And so it gives a false sense of progress, and it's ultimately a crutch. It does give like really fast demos.
And the autonomous driving you just do with some sensors, LiDAR, radar, etc. this, or do you need more?
We believe just cameras are the way to go.
Okay.
We don't use LiDAR at all. The entire road network is designed for passive optical, essentially vision. So in order to make a car drive properly, you have to solve vision. And at the point at which you solve vision, You really don't need any other instruments.
Okay.
Like a careful human driver, can drive with an extremely good track record. And unlike a computer, unlike a human, the computer does not get tired. It has 360-degree surround cameras. It's got 3 cameras pointing forward. So it's like being able to see with the eyes in the back of your head, basically. So it's really, vision is the way to go. There's some value to active optical for a wavelength that's occlusion penetrating, so it can see through fog or rain or dust. But it has to be high resolution, such that you can rely on, like for example, for radar at roughly 4 millimeter wavelength. This is good for occlusion penetration. But it needs to have enough resolution to know that you're braking for a real object and not just a bridge or a manhole cover or something like that.
So let's have a look now. We've had a look at a couple of simple robots and had a look at some of the complexities that people such as Elon Musk's company is trying to cope with. This is a little device called a McQueen robot from DF Robot, and we can use that to move around. It's got a line following capability if you wanted to use that, but it's also got the ultrasonics. You can see the 2 little barrels up the top. They're not eyes. One sends the sound signal out and the other one measures how long it took to get back. And it comes with a bunch of things. One of the things in colour down the bottom in the lowest hexagon there is a microbit. And if you're not familiar with these, they're very useful for kids to program in lots of different ways, and you would have seen them in the earlier video that I made about what happens after Scratch. So the schools bought this microbit thing, and now they can buy this other thing now and then use the same schools, the same expenditure to put it into the DF robot and give the robot a brain, and we can then program it to do a bunch of different things. But as we've seen, ultrasonics and line following is only really useful in certain contexts and environments. So the same device now, we can put a husky lens sitting on top, which will read QR codes, do facial and object recognition, which is really amazing. It's got built-in AI that enables it to be trained on what to see and what to recognize and what to do as a result of that. So you can see now that the school has got a sort of a sequential approach to procurement of these sorts of devices. So we start out with a microbit that is $25, and we buy those for the year 3s and 4s, and then the 5s and 6s, when they get into 5 and 6, or the 5s and 6s, can get the McQueen robot, and then the 6s and maybe 7s and 8s can use the husky lens and AI as it becomes more understandable to the kids. And of course there's nothing wrong with a year 3 kid using AI either, but the kid may not be at the stage of cognitive development or understanding, but never let that stop you. They can do some amazing things, kids. So you can see an interesting approach now to where the long-term usefulness of stuff is being considered, so that we're not just having something that we use in period 4 in week 2 of term 2 and then it goes in a cupboard for the rest of the year. It's got a lot more life and a lot more things that can actually be done with it. This next little video that we're popping up here runs for 4 minutes 35, and it talks about the next steps. So watch this by all means, or skip ahead.
Hey guys, I'm Ollie from Kai's Clan. Today, I'm going to show you an exciting virtual reality coding experience on Mars.
Ignition sequence start.
Kai's Clan is an exciting collaborative coding and robotics platform with AR and VR for kids aged 7 to 17. It was created so that teachers could have a more immersive, engaging way to teach coding. This is Kai. Kai's a versatile little robot. He works really well with students to solve a variety of real-world problems. We have an exciting mission on Mars here. Scientists predict a dust storm is coming. We need to send a rover out urgently to retrieve a fuel supply crate. If we don't get it back, our rocket ship can't return to Earth. It's almost time to show you our coding interface, but first, this is our Mars Discovery mission. This is the rover we'll be controlling today. We need to take that around here to the fuel supply crate, pick it up, and then take it back to our settlement. This is our coding interface. On the left, we have our coding blocks, just like Scratch or Blockly. In the middle, we have our run block, where we put our coding blocks to build our code. And on the right, we have a real-time view of what's happening on the adventure map. To start with, let's just code a basic movement. Let's get our rover to move forward 10 centimeters, and then move backwards 10 centimeters. So we put the blocks in here, enter our values, and then click run. Now let's build the code to get that fuel supply crate back. To start with, we're going to use pathfinding to get to a position close to the crate. So let's say X50, Y70. Next, we need to make sure our grippers are open so that we can grab the crate. Then we need to go to the position of the crate. We can use this block here, which lets us stop at a short distance so we don't crash into it. And then we're going to use the position of the crate. So we get that number 113 and find that here. Next, we need to close our grippers. I'm just going to copy and paste that block, change the value here. Once that's done, we just need to get down to the settlement here to drop the crate off. So I'll put a map mark here, and we can use that in our code. Position of map mark. Once we're there, we just need to release the crate. So I'll copy paste this one again to open the grippers, and then we'll just back up slightly. 10 centimeters will be enough. Okay, that's all looking pretty good. Let's test our code. So here we go. You can see the rover's using pathfinding to avoid those cliffs, heading towards the ice. The grippers are open, and you can see here on the blocks, as each command is executed, it's highlighted. So far, so good. There we go. Mission accomplished. Now, let's watch our coding come to life in AR.
8.5 down, 20 feet. 15 forward. 11 forward, come down nicely, 200 feet. 4.5 down, 5.5 down.
AR makes sharing your coding adventure easy. A teacher on the other side of the world can print this mat out and watch through AR in real time. Because Kai's Clan is web-based, you can share your classroom code with another school and collaborate on AR and VR coding adventures. As you can see, with Kai's Clan, it's very easy to get started in coding with AR and VR, and it's a lot of fun. You're not stuck here on Mars either. There are a bunch of different adventure mats, each with their own unique content. In the coming months, I'll be doing a full in-depth overview of Kai's Clan, along with a bunch of cool videos and activities. Until then, follow us on social media to stay in the loop. Thanks for watching, and I'll see you soon.
So there you go. Now you can see where this is heading. Those little devices can actually carry microbits as well, by the way. So let's look at some literature here, and the one that I've chosen is written by a guy called Pierre Lénard, French dude, and he covers a lot of things here about its use, robots as classroom assistants. A lot of people think that robots will replace teachers. There's a lot of discussion out there about that, but also about the sorts of things that we've been referring to here with the cognitive skills that can be developed in students and their understanding of their world, of mathematics, etc., and science. So this is something that is worth a read if you get a chance. It is written by, as I said, the French guy, and everything's in French, although this is translated here. You can grab the book from Springer. I don't think it actually costs anything. But some of the references that are within it are really quite cool. And this one here, looking at the difference between computer science, what in Australia we would call digital technologies, part of the digital technologies curriculum in the Australian curriculum, and information communications technology, ICT, which is nowadays in the curriculum referred to as digital literacy. You'll notice that there are 3 flag icons up the top, so if you happen to go and grab something and it's in French, then you can translate that into English by clicking on the Union Jack, or German if you feel like that. So what I've tried to do is to give an overview of the sorts of things of developing that whole idea of robotics from the very, very early moving something around a floor mat or something similar, through to some quite complex stuff such as that Kai's Clan thing, which will include virtual reality, artificial reality, augmented reality, the ability for a school in Sydney to work on the same project at the same time as a school in Melbourne, or Reykjavik in Iceland, doesn't really matter, although they'd have to get up quite early, I suppose, to do that. So lots and lots and lots of really interesting possibilities, but the key points are, don't get pulled in by bandwagons. Think of the cognitive value, the learning value in the use of these things, the sorts of things you need to be aware of before deploying in a classroom, and the ability to move kids up the scale, as it were, from a very elementary understanding of how these things work to a quite sophisticated problem-solving environment that is going to help them understand their world. Good on you.